Hello, welcome to the second part of our unit on electric potential. In this section, we're going to be looking more specifically at electric potential due to a point charge, but I'm going to begin with a couple of cautionary tales. The first cautionary tale is another case of alphabet soup. We encountered this with E's last section with electric potential energy. There's two E's there, an electric field, which is another E. We also saw little v for velocity and big V for voltage. We've got a similar problem here. We could have an equation that looks like this. V equals 5V, and those two V's are not the same. This V is the variable voltage, otherwise known as electric potential. This V is the unit volts. So how do you keep them straight? We now have three V's. We have a V for velocity, a V for voltage, and a V for volts. To me, I don't get confused. I can look at this and say, oh, I know what's going on. If I have a little v equals something with a big V in it. Obviously, there has to be a something here, so I'm going to add a squiggle to be the something. That to me, I can tell it apart. I can figure out what's going on. But I can definitely appreciate and understand where a student new to the material could find this very, very confusing. So I'm going to go back to what I said in the last. Here are three distinct V's. One with one flag, one with two flags, one with no flags, that you can use to distinguish between velocity, voltage, and volts. Okay, so that was cautionary tale number one. Here is cautionary tale number two. We have two things here. We have the electron volt, EV, and we have the volt. We already saw in the last slide that this guy is the unit for voltage. This guy is actually a unit of energy. And I know it has the name volt in it, or the word volt in it, but it's a unit of energy. And by definition, the unit conversion, 1 EV, is 1.6 times 10 to the minus 19 joules. And you'll be like, well, that's a very familiar number. Yes, that's a very familiar number. Electron volts are used for energies when atomic particles are in play, because the Q is so small that it throws everything tiny. So they made a tiny unit to go with it. So there you go. Don't get confused with your units. I'm trying to help. Okay, so now on to the electric potential due to a point charge. Remember, last section we saw that potential was field times a distance. And there was this caveat that you had to be moving in the direction of the field in order to get a change in potential. So it shouldn't really surprise you that the formula for calculating the potential due to a point charge is going to differ from the formula for calculating the electric field due to the point charge by one factor of distance. Okay, so here we go. V equals KQ over R. One factor of R different. One factor of R less, if you will. The other thing you will notice is there's no absolute value signs. And that is on purpose. Okay, so as an aside, remember we had this guy, E equals K, and there was an absolute value sign of Q over R squared. So you can really see the factor of R that's different in these two cases. Why did we put absolute value signs around that Q? Do you remember? It had everything to do with the fact that the electric field was a vector, and we didn't want a negative sign due to a charge to goof up our directions. So we absolute valued it and then used out of positive and into negative to figure out directions. That was field because it's a vector. We're now on potential. And remember, electric potential or voltage is really just electric potential energy with a factor of charge removed. It's an energy, and energy is a scalar. Scalars don't have directions, so I don't have to worry about directions. And because of that, I need that Q to not be absolute valued. If I have a negative charge, I need that to lead to a negative potential. Otherwise, it's not going to work properly. Okay, so no absolute value here. To finish this section off, let's just go and again take a look at what some potentials look like. We will look at more shortly in the next section as well. But let's start here. So this is the same simulation or visualization that we used in the last unit for electric field. Just to show you, remember it does this. Red means positive, blue means negative, and you could get all these really pretty patterns. Okay. Let's now turn on the equipotential lines. Okay. And let's start with a positive, a big positive charge. There it is. Okay, so what do we see? We see the white lines are the field lines, and the potential lines are circles surrounding my charge. Okay. And anywhere on this circle, the electric potential will be the same, which is consistent with a couple of things. The first thing it's consistent with is the V equals KQ over R portion. In order to get V to be constant, I need R to be constant. So that's a constant radius, if you will. The other thing that it is consistent with was the definition of electric field. Oh, nope. Flip that around. The definition of electric potential, V, equaling ED that we had in the last unit. And there was this statement I made that was, yes, good, but it required that the motion, in order to get a change in potential, be parallel to the electric field. And if my motion was perpendicular to the electric field, I got no change in potential. So if you look everywhere on here, the field and the potential are perpendicular to each other. Everywhere on there. Since the field is pointing radially outward everywhere, in order to be perpendicular everywhere, I get circles. Okay, let's turn off the field for a moment. Oop, I turned off the wrong one. Let's turn off the field. So there is the potential due to a large positive charge. Let's add a second large positive charge to the mix. Okay. So this looks a lot like what I drew for the mountain and the valley in the last section. But in that section, we went up and we went down. In this case, this is like having two mountains side by side. Okay, which means in the middle here, there's no, or potentially no zero. If I want to get a zero in between my two charges for potential, I've got to go from positive to negative. So to get from large positive to large negative, I've got to go through zero, and you can see I've changed color. Okay. So potential behaves very differently from what field did. And part of that, a good portion of that, is the fact that it is a scalar as opposed to field, which is a vector. We will look into this more in the next unit.